I'm part of the product management team here at MapleSoft. I spend a lot of my time talking to our customers and helping them to better understand and use our tools, technologies and services. Today, this webinar is about engineering optimization. Specifically, we'll be walking through 3 applications in detail. First of all, we'll be minimizing the production cost of a welded beam. Then we'll be minimizing the weight of a coil spring given conditions on its loading. And then to finish off with, we'll find the best packing of discs of varying radii that fits into a circular container. The first 2 applications employ Maple's local optimizers, while the third is a tough global optimization problem. All of these applications are available on the Maple Application Center for you to download. So I've chosen to highlight those 3 engineering optimization applications. However, Maple is regularly applied across a wide range of other optimization applications as well. Everything from optimizing asset portfolios to minimize risk and maximize returns, to determining the molecular structure of a molecule by minimizing the total free energy, or to fine-tune the control strategy of a robot arm manipulator. As I said previously, in the 3 applications I'll be demonstrating, we'll be using Maple's local optimizers and the global optimization toolbox. For the local optimizer, we need to specify an objective function. This will be something like the cost or the weight. We'll also need to specify constraints. Those constraints will be engineering restrictions, such as limits on the shear stress or geometrical constraints. For the packing problem, we'll use the global optimization toolbox. In addition to the objective function and the constraints, we'll also need to place bounds on the search space for the optimizers. The local optimizers are gradient-based, but the global optimization toolbox is based on a type of genetic algorithm known as differential evolution. So let's start looking at the first application. We're looking at a welded beam with a load applied to one end. The total cost of producing this beam is the sum of the cost of the labour required for the weld and the material cost as well. We want to minimise this total cost by varying the weld dimensions, as illustrated here on the slide. However, we also want to respect a series of constraints. These constraints include limits on the shear stress, the bending stress, the buckling load, and the end deflection. So let's jump into the worksheets. This presentation is meant to be an introduction to Maple, so I'll assume some basic knowledge of the system. At the top of the worksheet we have a title, diagram and a description of the problem domain. And here we have our system parameters. So parameters such as Young's modulus, the shear modulus, the overhang of the member, the design stress of the weld, the normal stress for the material, the maximum deflection allowable, and the load applied to the end of the member. And finally, we have the cost per unit volume of the weld material, the cost per unit volume of the bar, and the labour cost per unit weld volume. And then we define a cost function. This is what we'll be minimising. We calculate the volume of the weld material, the volume of the bar, hence the total material cost to be minimised is the sum of these quantities. And then we have a series of engineering relationships. We have the primary stress acting over the weld throws, the secondary torsional stress, the moment of the load P about the centre of gravity of the weld, the polar moment of inertia of the world, and so on. All of these constraints are entered here in proper mathematical notation, so this is very readable, very understandable. And at the bottom we've used Maple's optimization functionality to minimize the objective function. That's the total cost of producing the weld beam while respecting our constraints. The system variables are simply x1, x2, x3 and x4. So Maple has minimized the total cost of producing the weld by varying those dimensional parameters. One of the benefits of using a system like Maple is that you can change some system parameters. Let's say that we change our shear modulus, change the overhang length, and so on. If I hit this button, those changes cascade down the length of my Maple worksheet. Maple updates all of my results and my dependencies, so I have a new set of optimized parameters. Let's look at another optimization problem. This one is somewhat similar. Here we're minimizing the weight, the mass of a spring by varying the dimensions and the number of coils while respecting a number of constraints. It's loaded at one end and we want to minimize its mass by varying the number of coils, the coil diameter and the spring diameter. The constraints include the minimum deflection, the minimum search wave frequency and an upper limit on the stress as well. And this is the application. Again, it follows a similar design to the previous welded beam application. At the top I have a diagram and a description of the problem domain. I then have some parameters such as the weight density of the spring material, the shear modulus, the allowable shear stress. I then have a number of engineering relationships and constraints that have to be respected. The constraints include things like the minimum deflection, the outer diameter of the spring, and a limit on the shear stress. I then have an objective function which gives me the weight of the spring, and then I use Maple to minimize the mass by varying a number of parameters such as the coil diameter, the spring diameter and the number of coils. And again, Maple gives me optimized design parameters. So in both this application and the previous application I've used this function minimize from Maple's optimization package. This is a pretty intelligent solver. It actually cycles through a number of algorithms and picks the best one for the application. If I want to peek under the hood and see what minimize is doing, I can do that by raising the info level of the optimization package. Let's make that equal to, I think, 3. So now if I rerun the application, I have a bit more information about what's going on under the hood, including certain tolerances. And Maple's also told me which optimization method it's using. Here it's using the SQP method, which is sequential quadratic programming. Let's move on to our final application. In this application, we'll be finding the best packing of a shape to minimize the size of a container. There are many variants of this problem. We could find the best packing of circles in an oval or in a square. We could find the best packing of spheres in a cylinder or a box. However, in this application, we'll be finding the best packing of discs in a containing circle. There are many applications which use these principles. For example, the coverage of a geographical area with cell transmitters, packing cans into a smallest box, planting trees to maximize forest density and distance between trees, cable bundling, cutting discs from a material but to from a given material but minimizing waste, and also other neat applications such as origami design. Let's go through some of the math of this application. So as I said, we want to minimize the size of the circular container by finding the best packing of discs inside the container. The discs must of course be inside the container and they can't overlap. So let's see how we mathematically specify these constraints. So let's look at the no overlap constraint. We have two circles, circle 1 and circle 2. The origin of circle 1 is at x1, y1 and it has a radius of r1. The origin of circle 2 is at x2, y2 and it has a radius of r2. The distance between the origins of both circles is simply the square root of dx squared plus dy squared. The minimum distance between these two circles will be a line connecting 2 points on their circumferences. The length of this line will be the square root of dx squared plus dy squared minus the radius of the first circle minus the radius of the second circle. If these two circles do not overlap, then this length has to be greater than 0. This constraint is iterated across all pairs of circles. Now, because Maple is a symbolic math tool, we don't have to write this large series of constraints manually. We can programmatically generate this entire series of symbolic constraints using Maple's symbolic programming commands. So let's look at the application. Again, I have a title and a description and a diagram of the problem domain. The diagram illustrates one potential solution for this problem. As you can see, I found the best packing of, I think, 50 circles, 50 discs in a circular container here. This application uses the global optimization toolbox, and we're working with 50 randomly generated circles, and the radius of circle n is equal to n. So what I'm going to vary are the coordinates of the center of the discs and the radius of the circumscribing circle. And these are my constraints. For example, this constraint is the no overlap constraint that I described on the slide. This constraint is iterated across all pairs of circles, and I've generated this large series of constraints with Maple's symbolic programming commands. If I actually want to see the equations that Maple has generated, all I have to do is delete this colon and hit enter. And we just give Maple a few seconds and it just shows us all of the equations that it programmatically generated. There we go. I then collect together my series of constraints, and then I ask Maple's global optimizer to minimize the radius of the constraining circle while respecting my constraints. Now, I'm not going to run this application because it takes about 2 minutes or so to optimize the whole system, but these are the generated results. Maple varies the position of the disks and minimizes the radius of the containing circle. Now, there are many variants of this problem. For example, I could do sphere packing in a sphere. Again, this uses the same mathematical principles, but it's in 3 dimensions and it's a bit more visually interesting. I can also do neat things like packing circles into an ellipse. This is a bit more mathematically involved. The constraints are somewhat more complex simply because we're trying to minimize the dimensions of an ellipse. And I can also do circle packing in a square as well. As I said, all of these applications are available for you to download on the Maple Application Center. So that was everything I wanted to speak about today. If you have any questions about any of the principles I've demonstrated, then feel free to contact us.